Now that we've defined how we're going to describe our kinematic motion in terms of omega, angular acceleration, and angular velocity, and alpha, angular acceleration, we're going to follow the same pattern we did for the whole semester, basically. So we're going to start with kinematics, which we already started with some, and in particular, we're going to say that look at the case where angular acceleration is constant. And really, we're just going to worry about whether it's positive or negative. So we're going to say like out of the screen or into the screen, positive or negative, and not worry about angular acceleration that's not along one of our main axes. If that's the case, then just like for the linear case, we had x is equal to x naught plus v naught t plus 1/2 a t squared when a was constant. Over here, that when alpha is constant, that gives us the same set of equations. Theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. It's really a one-to-one. We have angular displacement and linear displacement. We have angular initial speed right here and linear initial speed, and then the acceleration, which is constant. And then we have, of course, v is equal to v naught plus a t, and over here we have omega is equal to omega naught plus alpha t. And so over here, if we know the initial angular speed, so many radians a second, we know how long it's going and what the acceleration is, we can find the angular speed at any point down the line. So you might do something like this for a wheel that's starting to spin up to some speed, and once it gets to that speed, maybe your alpha is 0, because when your alpha is 0, notice your angular velocity stays the same, like a clock. A clock, we hope, has alpha equal to 0 because we want it to do the same number of revolutions in the same amount of time. Otherwise, it's going to be a clock that quickly gets out of sync. All right, our final equation is v squared, is solving for this, plugging it in here and doing some algebra, equals the initial velocity squared times 2a. I'm just going to write this as delta x. That would be x minus x naught if you like. And same thing over here, omega squared equals omega naught squared plus 2 alpha delta theta. And we can, in fact, connect these equations, right? If we have something that's rotating, I'll draw it down here, then we know that our theta and r and this distance s, they're connected. And in fact, we can say that the connection really between these two, I realize I've written this as x because that's our normal way of looking about it, but the connection between linear and angular variables is that s, the arc length, is equal to r times theta, and then we have a connection here that says v is equal to r omega. Similarly, we can have a connection that says a is equal to r alpha, but we have to be careful. This is the tangential acceleration. In other words, this is the tangential velocity, but that's less of an issue. That's just here, the tangent. The thing we need to worry about with the acceleration is this is the acceleration associated with speeding up or slowing down. So a sub t is if you're speeding up or slowing down along the curve. Because of course we still had an acceleration, right, when we were going around in the circle. That was the center seeking acceleration. Sorry, this AT and the VT should be in the same direction here. But we had AC, right? AC is our center pointing acceleration, and that's still equal to V squared over R which if we put in our equation for v, we can say this is r squared omega over r. So another way to write your AC, your centripetal acceleration, is v squared over r. Sorry, this v is beginning to look like an r. Or it's equal to, sorry, that's a squared, r omega squared. Those are two expressions, and that's always there. This depends on, like you're going around a curve, the traffic circle at Eckerd, it depends on whether you're putting on your brakes or speeding up. But if you're changing your speed along the direction of travel, in other words, along here, then you have a tangential acceleration. Generally, this centripetal is going to be fairly big in comparison with this. It just depends on how fast you're going. But overall, our net acceleration, right, for a car like this, if it's speeding up, if it has an AT, a tangential acceleration, and an AC, centripetal acceleration, then the net is going to be the sum of these, like this. And that's the direction our friction is going to have to work, right? It's going to be the sum of these two. If I move this AT here, that's the AT vector. And so this acceleration is the total acceleration, and your static friction is going to have to provide that if that's the force that's doing it. So AC, just for completeness, in terms of angular variables, is this. A sub t is r times alpha. So this could be constant, right, if alpha is constant, but this would be changing. As you get a higher and higher speed, the centripetal acceleration is going to be increasing, and so you need more and more friction to hold you to that road if you happen to be speeding up as you're going around the turns.